All right, now for some eigenvalues, eigenvectors, eigenanalysis is what our book calls it. Eigenanalysis and canonical factorizations, so section 3.8. There's a bunch of stuff in section 3.8, so it'll take several videos to get through this. So we'll define eigenvalues, eigenvectors. You're familiar with these ideas from sophomore linear algebra. We'll consider geometric and algebraic multiplicity of eigenvalues. You probably did that in sophomore linear algebra as well. Similar matrices, diagonalization of matrices. Here's something maybe a little bit new, orthogonal diagonalization of matrices. And something I'm virtually certain you didn't get to in linear algebra would be spectrum, spectral radius, and spectral decompositions. Okay, so the beginning will largely overlap, though not exclusively, with what you did in linear algebra. First, let A be an n by n matrix. Of course, eigenvalues and eigenvectors are only associated with square matrices. If V is an n vector, vector with n components, and C is a scalar satisfying A, matrix A times vector V equals scalar C times vector V, then V is called an eigenvector of A, and C is an eigenvalue, sometimes called, kind of commonly called characteristic value. We'll stick to the eigen terminology. So these are eigenvectors and eigenvalues of matrix A, and together the pair is called an eigenpair for matrix A. Okay, we'll be looking at zeros of polynomials, so complex numbers are going to arise potentially in the discussion. So what we'll do is make an agreement that we're dealing with real matrices, but complex numbers are part of the role. We said, let's see, we have this type of relationship here. We're not allowing the zero vector to count as an eigenvector. That leads to a world of troubles and colliding with the definition here. So we only consider non-zero eigenvectors. And we're letting zero potentially be an eigenvalue, and it can potentially have associated non-zero eigenvectors. All eigenvectors are non-zero. So a little comment there, don't allow the zero vector to count as an eigenvector, but the zero value can count as an eigenvalue. We'll take the matrices to have real entries, but we're going to allow eigenvalues and eigenvectors to be complex or to have complex entries. So complex numbers are lurking in the background. I'd be more than happy to just do everything with complex numbers, including having complex entries in the matrices. Our book, with an angle towards applications to statistics, doesn't quite go in that direction though. But it's unavoidable that the complex numbers will pop up in the setting of eigenvalues and eigenvectors. Definition, at A, B, and n by n matrix, if W is an n vector, non-zero n vector, and C is a scalar, satisfying W transpose times A equals C times W transpose, then W is called a left eigenvector of A. So there's something I doubt you did in linear algebra. So we have kind of regular eigenvectors and we have left eigenvectors. If W is a left eigenvector of A and A is symmetric, then what it amounts to is eigenvectors and left eigenvectors are the same when we have a symmetric matrix. So suppose we have W transpose A equals CW transpose. Suppose W is a left eigenvector of A. Let's take that equation and transpose both sides. Okay, W transpose A transpose will yield A transpose times W. Right-hand side, we've got just a scalar C. Remember, C is a scalar. The other stuff is vectors or matrices. So we'll have W transpose transpose, and that just produces a W. All right, so that gives us a relationship A transpose W equals CW. We're looking at a situation where A is symmetric in this little comment. So A transpose and A are the same thing, and that gives us A times W equals C times W. Well, that's the equation that needs to be satisfied for W to be an eigenvector of A with corresponding eigenvalue C. So W is an eigenvector of A as well. So if W is a left eigenvector of A is symmetric, then W is also a regular eigenvector. You know, the terminology right eigenvector doesn't seem to be a thing. So we refer to eigenvectors and left eigenvectors. But we get equality between those when we have a symmetric matrix. We'll see a handful of results here in the beginning about eigenvectors. First one, Theorem 3.8.1. If V is an eigenvector of matrix A and W is a left eigenvector of matrix A with a different associated eigenvalue, then those two eigenvectors are perpendicular. Well, I guess I should say that eigenvector is perpendicular to the left eigenvector, distinguishing between left eigenvectors and regular eigenvectors. So it's a claim of orthogonality. It's a claim of inner products being zero. All right, so we'll need the definition of eigenvector and left eigenvector. Let's look at a proof. Okay, so there's the claim. We've got a situation where V is an eigenvector of A. That means A times V equals some scalar multiple of V. Suppose the corresponding eigenvalue is C sub 1. W is a left eigenvector of A. Means W transpose A equals some scalar multiple of W transpose. Call it C sub 2. All right, so we've got the corresponding eigenvalues, C1, C2, different. So we've hypothesized that C1 and C2 are not equal. Okay, let's take W transpose A, this quantity. Let's multiply by vector V on the left on both sides of this equation. So that will give us W transpose A times vector V equals C sub 2 W transpose times vector V. Quick comment about concerns over conformability for matrix products. A is a square matrix, say n by n. So all these vectors have n components in them. So the dimensions are appropriate for the multiplication we're doing. All right, let's see, we can associate A and V. So this is the same as W transpose times AV. We know matrix A times vector V is scalar C sub 1 times vector V. So for the AV, we can substitute the C1V. Remember, C1's a scalar, so we can pull that out front. And we've got W transpose AV equal to this quantity, and W transpose AV equal to this quantity. Or these, are they vectors? Are they matrices? We're taking a transpose of a column vector. So this is a row vector times a column vector. These are one by one matrices if we'll interpret them as matrices. They're also interpreted in terms of inner product. So here comes the orthogonality. So anyhow, we've got C2 W transpose V equals C1 W transpose V. So we've got equality of these two one by one matrices, which I'd be happy to treat as scalars. Well, that's C1 times a scalar equals C2 times a scalar. Well, if C1 and C2 don't equal each other, the only way these products on both sides can be equal to each other is if this other quantity, W transpose V, is 0. So we must have W transpose V equals the number 0. Yeah, it's a matrix product way of expressing an inner product. That must be 0. Otherwise, we have absurd algebra over here. So the inner product of W and V must be 0. That is, W and V are orthogonal, and that was the claim. Some properties of eigenvalues and eigenvectors. is we'll start with matrix A to be, say, n by n matrix, square matrix, of course, with eigenpairs C and V. So V is an eigenvector with corresponding eigenvalues C. The claims are, and the proof of this is left as an exercise, claims are, for any non-zero scalar B, actually they're letting it be complex number here, B times V is an eigenvector of matrix A. Straightforward computation. We're saying a scalar multiple of an eigenvector is an eigenvector. The corresponding eigenvalue will be C. That's true, although that's not claimed here. For any non-zero scalar B, B times C is an eigenvalue of the matrix B times A. Okay, here in the second one, we've modified the eigenvalue of matrix A, and that's required us to modify the matrix itself. You multiply the eigenvalue by some scalar B, that requires a modification of the matrix by some scalar B. And we're getting in some weird mixed up settings here. This scalar B could be complex. So when I look at B times A, that's a matrix with some complex numbers in it. We could drop all this real restriction stuff and do all this just with complex numbers. It'd be cleaner, actually. If A is non-singular, that is, if A inverse exists, then 1 over C and V form an eigenpair of A inverse. So let's see, we had hypotheses of eigenvector, eigenvalue, matrix A. This is a claim that we've got eigenvector, eigenvalue for matrix A inverse, assuming invertibility. If A is square, C is non-zero, so we did allow 0 as an eigenvalue, but not in this claim. So eigenvalue of A, call it C, is non-zero. Then the claim is 1 over C and V are an eigenpair for the pseudo inverse of matrix A. So this is a pseudo result, I guess, with respect to part 3. So part 3, we had a nice invertible matrix. Well, if I don't have an invertible matrix, we know from a previous section or two, we always have a pseudo inverse of a matrix, even when they're not square. We got to have square matrices here, though. Without a square matrix, determinants don't make sense. And as we'll see, determinants, as you know, determinants are intimately involved in the computation of eigenvalues. But without square matrix, then the eigenvalue conversation doesn't make sense. So that has to be added as a hypothesis, but that's a moderately impressive result, I think. So we can extract some eigenvalues for the pseudo inverse of matrix A based on the eigenvalues of matrix A and eigenvectors. If A is diagonal or triangular with diagonal entries A sub I, then the eigenvalues of matrix A are those diagonal entries. No claim in general about eigenvectors, but if A is diagonal, forget the triangular part, so additional hypotheses really. If A is diagonal, the corresponding eigenvectors are the E sub i's, the ith unit vector in Rn, the ith standard basis vector in Rn, provided we had a diagonal matrix. C to the K and V are an eigenpair for the matrix A to the K, where K is any natural number. You probably ran across that in linear algebra. It's a common little homework exercise, straightforward computation to establish part 6. Another claim, if A is n by m matrix and B is an m by n matrix, then the non-zero eigenvalues of the product, A times B, are the same as the non-zero eigenvalues of B times A. Okay, AB, BA, both of them are square matrices. We get this relationship between eigenvalues between those matrices, non-zero eigenvalues. If m equals n, so we're talking 2 square matrices here, then the claim is the eigenvalues of AB and the eigenvalues of BA are the same. The non-zero part is dropped in the second case where we have square matrices. Just a little quick note. whenever we said eigenvalues, still, it was always with square matrices. B times A is a square matrix. A times B is a square matrix, even though A and B themselves are not square matrices. And finally, in the list of claims, if A and B are n by n matrices and B inverse exists, then the eigenvalues of B, A, B inverse are the same as the eigenvalues of matrix A. This might remind you of a topic of similar matrices from linear algebra. So we get an equality of the eigenvalues between matrix A and this particular matrix here, sort of based on matrix A through some invertible matrix B. Proof of these is to be given in exercise 316. Parts of them follow straight from the definition of eigenvalue and eigenvector. Some others will be based on some determinant properties that we're about to see. Corollary to that result, a very useful corollary, is the set of eigenvectors of a square matrix A associated with a given fixed eigenvalue C, along with a zero vector. So we're taking all the eigenvectors associated with C and we're throwing the zero vector in because it doesn't count as an eigenvector. These form a subspace of Cn. So we very much got the complex thing going on. We could say a subspace of Rn if we were fortunate enough that in this conversation of eigenvectors and eigenvalues, it happened to be restricted to real numbers. So we're getting that eigenvectors form a subspace. This subspace is called the eigenspace of A, associated with eigenvalue C. Now, this has loads of applications in differential equations. You get solutions, if you can couch the equation in the right language, you get solutions to systems of differential equations coming out as eigenspaces. So this is a common applied math idea of an eigenspace. So we want to show that we've got an eigenspace, a vector space, and it's claimed to be a subspace of Rn or Cn. All we got to do is show closure under linear combinations. Okay, by the definition of a vector space of n vectors from Rn, which would do just the same as a definition for a subspace of Cn, it would do for a subspace of Fn, where F is any field. But we need to show closure under linear combinations. We need to show for any scalars A and B and any vectors, in this case eigenvectors of matrix A, say V1 and V2, we have that AV1 plus BV2 is either an eigenvector of A with associated eigenvalue C, or it's the zero vector. Okay, so let's take AV1 plus BV2 and let's multiply it on the left by matrix A. You got your linearity properties when you multiply, so we can distribute and bring the scalars out front. All right, now we've got A times V1. Well, V1 is an eigenvector of matrix A with associated eigenvalue C. So A times V1 is C times V1. Similarly, matrix A times vector V2 is scalar C times vector V2 because these are eigenvectors with eigenvalue C. We can, let's see, pull the C out front and do some rearranging with the scalars, and we get C times AV1 plus BV2. So we've shown that this vector, AV1 plus BV2, when multiplied on the left by A, gives scalar C times that vector. That means this vector, AV1 plus BV2, that means it's an eigenvector of matrix A, unless it's a zero vector. So it's either an eigenvector or else it's the zero vector and doesn't count as an eigenvector. But that's what we were trying to show. We're taking the collection of all eigenvectors associated with C along with the zero vector. So we are getting the closure under linear combinations of that set. We've got the closure we need, and by the definition, we've got a subspace of the appropriate vector space, Rn, Cn, Fn. Okay, so let's introduce some more ideas. Actually computing eigenvalues and eigenvectors is, we're not going to get that hands-on with this stuff. That's linear algebra stuff. It's undergraduate stuff. But when you do compute these things, you use determinants, and here's why. If C and V are an eigenpair for a square matrix A, then by definition, AV equals CV, definition of eigenpair. Oh, and V has to be a non-zero vector. We could take this equation and rearrange it as AV minus CV equals a zero vector. We could factor the V vector out on the right from this. Distribution backwards, of course, have to introduce this identity matrix using a slightly different font for identity matrix in the setting of eigenvalues and eigenvectors. That's just my doing. But we have then A minus C times the identity matrix times vector V equals 0. I can observe a handful of things. One of them is, hey, that means V is in the null space of this matrix, A minus Ci. Alternatively, I could look at this as if it were a system of equations with the V's as maybe unknowns. Now I know if A minus Ci is non-singular, that is if the coefficient matrix over here is invertible, then we could just multiply on the left both sides of this equation by that inverse, and we would see that V has to be the zero vector. But you don't count the zero vector as an eigenvector, so we can't have that. We must not have that A minus Ci is non-singular. We must have that it is singular when V is an eigenvector. So that leads us to consider the equation singular determinant of A minus Ci equals 0. Now, I should have commented earlier, of course, this is a lambda has been replaced with C in our setting here. Okay, for n by n matrix A, the n-degree polynomial of C, determinant A minus C times I, is called the characteristic polynomial, just like it was in linear algebra. Setting the characteristic polynomial equal to 0 is called the characteristic equation. So P sub A for matrix A, P for polynomial, and think of C as an unknown. And this is how you compute eigenvalues in the setting of linear algebra. Now, some texts take the characteristic equation as determinant of Ci minus A instead of A minus Ci. That won't affect eigenvalues, that won't affect eigenvectors. It will affect something we're going to do called companion matrix here in the near future. Here's your reference, actually quite a good matrix analysis book, Theory of Matrices book. It's a bit more theoretical. They don't have an eye towards applications to statistics like we're trying to do with the Gentle book. But they take this as their definition of characteristic polynomial and associated characteristic equation. Well, that's gonna give us a relationship between this idea of a polynomial and our definition of the characteristic polynomial, where they're differing by a negative sign. So how are determinants related when you change matrices by a negative sign? Yeah, you pick up a power of -1. I guess it was theorem 3.1.b that tells us that. So our characteristic polynomial is related to Horn and Johnson's characteristic polynomial by a power of -1. They're the same when n is even, and they differ by negative when n is odd. So that resolves that if you read different references. A useful observation, I've labeled this note 3.8a. I've given it a name, so we'll refer back to it at some point in the future. If we calculate the determinant of A minus Ci, then by definition, we're going to get this stuff with a symmetry group, S sub n, and the permutations and all of that, where the B sub I pi of I is the I pi of I entry of the matrix. Okay, the matrix we're taking a determinant of here is A minus Ci in this case. I want to see the form of that matrix. I'm sorry, the form of that polynomial that'll result, the form of that determinant in terms of C. If pi is the identity in S sub n, identity, it's an even permutation, sigma of the identity equals 1. So the sigma of pi will just produce a plus sign up front. But what's going to happen is if we've got the identity, then we're going down this matrix, picking up I, as I ranges from 1 to n. So B11, B22, B33. We're going down the diagonal when we use the identity permutation of this matrix. The diagonal entries of this matrix are A sub I minus C. So we get A sub I minus C along the diagonal of that matrix. And when we look at this particular expression in the big summation for the determinant of that matrix, this includes a term of the form negative C to the n. We're going to multiply this thing out. We get a bunch of terms, but one of them is negative C times itself n times because we're taking a product. So we'll have a negative 1 to the n, C to the n term that pops up from here. That'll be the highest power of C generated. In fact, if we don't take the identity, the highest power of C would be less than that, at most n minus 1. For some technical reasons, it's actually at most n minus 2. But the highest power of C is C to the n, and the only place we get it is from that previous argument when we're dealing with the identity permutation. So the determinant of A minus Ci is an n-degree polynomial. The coefficient of C to the n is negative 1 to the n, as just argued, when A is an n by n matrix. So we're getting out, as you knew, for an n by n matrix, an n-degree polynomial, and by the way, we know what the leading coefficient is. An n-degree polynomial in the unknown C, or unknown lambda is the way you dealt with it in linear algebra. So can you find n roots for an n-degree polynomial? Fundamental theorem of algebra says I can if you'll let me count things a certain way. Every eigenvalue of matrix A is a root of the characteristic polynomial and a solution of the characteristic equation. Fundamental theorem of algebra tells you you're going to have n eigenvalues if you'll count multiplicity and you'll let me use complex numbers. So this is where the unavoidability of complex numbers comes in the conversation of eigenvalues. Fundamental theorem of algebra tells you n-degree polynomial has n roots, counting multiplicity. But you're going to have to use complex numbers for those zeros to exist, those roots of that polynomial to exist, for those eigenvalues to exist. So that's where the complex numbers are unavoidable. We're going to take the characteristic polynomial. This is a classical result. I bet you this is in your linear algebra book, whether you had time to cover it or not, I don't know. Called the Cayley-Hamilton theorem. It says if we take matrix A and it has characteristic polynomial P sub A, if we'll apply that polynomial to matrix A, we get out the zero matrix. It makes sense to apply polynomials to matrices. We observed this in, I think, the last section. You can raise a matrix to powers, you can multiply them by scalars, and you can add them together. So it makes sense to evaluate a polynomial at a matrix. Claim is, when we evaluate a matrix at its characteristic polynomial, we get out the zero matrix.